Real-time locating systems are used to automatically identify and track the location of objects or people in real time, usually within a building or other contained area. Wireless RTLS tags are attached to objects or worn by people, and in most RTLS, fixed reference points receive wireless signals from tags to determine their location. Examples of real-time locating systems include tracking automobiles through an assembly line, locating pallets of merchandise in a warehouse, or finding medical equipment in a hospital. The physical layer of RTLS technology is usually some form of radio frequency communication, but some systems use optical or acoustic technology instead of or in addition to RF. Tags and fixed reference points can be transmitters, receivers, or both, resulting in numerous possible technology combinations. RTLS are a form of local positioning system, and do not usually refer to GPS, mobile phone tracking. Location information usually does not include speed, direction, or spatial orientation. Origin: the term RTLS was created at the ID Expo trade show by Tim Harrington, Jay Werb and Bert Moore. It was created to describe and differentiate an emerging technology that not only provided the automatic identification capabilities of active RFID tags, but also added the ability to view the location on a computer screen. It was at this show that the first examples of a commercial radio-based RTLS system were shown by Pinpoint and WareNet. Although this capability had been utilized previously by military and government agencies, the technology had been too expensive for commercial purposes. In the early 1990s, the first commercial RTLS were installed at 3 healthcare facilities in the United States, and were based on the transmission and decoding of infrared light signals from actively transmitting tags. Since then, new technology has emerged that also enables RTLS to be applied to passive tag applications. Locating concepts: RTLS are generally used in indoor and/or confined areas, such as buildings, and do not provide global coverage like GPS. RTLS tags are affixed to mobile items to be tracked or managed. RTLS reference points, which can be either transmitters or receivers, are spaced throughout a building to provide the desired tag coverage. In most cases, the more RTLS reference points that are installed, the better the location accuracy, until the technology limitations are reached. A number of disparate system designs are all referred to as real-time locating systems, but there are 2 primary system design elements. Locating at choke points. The simplest form of choke point locating is where short-range ID signals from a moving tag are received by a single fixed reader in a sensory network, thus indicating the location coincidence of reader and tag. Alternately, a choke point identifier can be received by the moving tag, and then relayed, usually via a second wireless channel, to a location processor. Accuracy is usually defined by the sphere spanned with the reach of a choke point transmitter or receiver. The use of directional antennas, or technologies such as infrared or ultrasound that are blocked by room partitions, can support choke points of various geometries. Locating in relative coordinates. ID signals from a tag is received by a multiplicity of readers in a sensory network, and a position is estimated using one or more locating algorithms, such as trilateration, multilateration, or triangulation. Equivalently, ID signals from several RTLS reference points can be received by a tag, and relayed back to a location processor. Localization with multiple reference points requires that distances between reference points in the sensory network be known in order to precisely locate a tag, and the determination of distances is called ranging. Another way to calculate relative location is if mobile tags communicate directly with each other, then relay this information to a location processor. Location accuracy. RF trilateration uses estimated ranges from multiple receivers to estimate the location of a tag. RF triangulation uses the angles at which the RF signals arrive at multiple receivers to estimate the location of a tag. Many obstructions, such as walls or furniture, can distort the estimated range and angle readings, leading to varied qualities of location estimate. Estimation-based locating is often measured in accuracy for a given distance, such as 90% accurate for 10-meter range. Systems that use locating technologies that do not go through walls, such as infrared or ultrasound, tend to be more accurate in an indoor environment because only tags and receivers that have line of sight can communicate. Applications: RTLS can be used numerous logistical or operational areas such as locate and manage assets within a facility, such as finding a misplaced tool cart in a warehouse or medical equipment, notification of new locations, such as an alert if a tool cart improperly has left the facility, to combine identity of multiple items placed in a single location, such as on a pallet, to locate customers, for example in a restaurant, for delivery of food or service, to maintain proper staffing levels of operational areas, such as ensuring guards are in the proper locations in a correctional facility. To quickly and automatically account for all staff after or during an emergency evacuation, to automatically track and time-stamp the progress of people or assets through a process, such as following a patient's emergency room wait time, time spent in the operating room, and total time until discharge. Such a system can be used for process improvement, clinical-grade locating to support acute care capacity management. Privacy concerns: RTLS may be seen as a threat to privacy when used to determine the location of people. The newly declared human right of informational self-determination (d. Informational Selbstbestimmung) gives the right to prevent one's identity and personal data from being disclosed to others, and also covers disclosure of locality, though this does not generally apply to the workplace. Several prominent labor unions have come out against the use of RTLS systems to track workers, calling them the beginning of Big Brother, and an invasion of privacy. However, this loss of privacy may be outweighed by other benefits to staff. For example, Toronto General Hospital is looking at a TLS to reduce quarantine times after an infectious disease outbreak. After a recent SARS outbreak, 1% of all staff were quarantined, and more accurate data regarding who had been exposed to the virus could have reduced the need for quarantines. Types of technologies used: there is a wide variety of systems, concepts and designs to provide real-time locating. Active radio frequency identification, active radio frequency identification, infrared hybrid, infrared, second-generation infrared, optical locating, low-frequency signpost identification, semi-active radio frequency identification, passive RFID RTLS locating via steerable phased array antennae, radio beacon, ultrasound identification, ultrasonic ranging, ultra-wideband, wide over narrow band, wireless local area network, Bluetooth, clustering in noisy ambience, bivalent systems. A general model for selection of the best solution for a locating problem has been constructed at the Radboud University of Nijmegen. Many of these references do not comply with the definitions given in international standardization with ISO IEC 19762-5 and ISO IEC 24730-1. However, some aspects of real-time performance are served and aspects of locating are addressed in context of absolute coordinates. Ranging and angulating, depending on the physical technology used, at least one and often some combination of ranging and/or angulating methods are used to determine location, angle of arrival, line of sight, time of arrival, multilateration, time of flight, two-way ranging according to Nanotrona Euro unregistered trademark S patents, symmetrical double-sided Euro two-way ranging, near-field electromagnetic ranging. Errors and accuracy in locating systems. Real-time locating is affected by a variety of errors. Many of the major reasons relate to the physics of the locating system, and may not be reduced by improving the technical equipment. None or no direct response. Many RTLS systems require direct and clear line-of-sight visibility. For those systems, where there is no visibility from mobile tags to fixed nodes, there will be no result or a non-valid result from locating engine. This applies to satellite locating as well as other RTLS systems such as angle of arrival and time of arrival. Fingerprinting is a way to overcome the visibility issue. If the locations in the tracking area contain distinct measurement fingerprints, line of sight is not necessarily needed. For example, if each location contains a unique combination of signal strength readings from transmitters, the location system will function properly. This is true, for example, with some Wi-Fi-based Rtls solutions. However, having distinct signal strength fingerprints in each location typically requires a fairly high saturation of transmitters. False location: the measured location may appear entirely faulty. This is a generally result of simple operational models to compensate for the plurality of error sources. It proves impossible to serve proper location after ignoring the errors. Locating backlog: real-time is no registered branding and has no inherent quality. A variety of offers sales under this term. As motion causes location changes, inevitably the latency time to compute a new location may be dominant with regard to motion. Either an Rtls system that requires waiting for new results is not worth the money, or the operational concept that asks for faster location updates does not comply with the chosen system's approach. Temporary location error: location will never be reported exactly, as the term real-time and the term precision directly contradict in aspects of measurement theory, as well as the term precision and the term cost contradict in aspects of economy. That is no exclusion of precision, but the limitations with higher speed are inevitable. Steady location error: recognizing a reported location steadily apart from physical presence generally indicates the problem of insufficient overdetermination and missing of visibility along at least one link from resident anchors to mobile transponders. Such effect is caused also by insufficient concepts to compensate for calibration needs. Location jitter: noise from various sources has an erratic influence on stability of results. The aim to provide a steady appearance increases the latency contradicting to real-time requirements. Location jump: as objects containing mass have limitations to jump, such effects are mostly beyond physical reality. Jumps of reported location not visible with the object itself generally indicate improper modeling with the location engine. Such effect is caused by changing dominance of various secondary responses. Location creep: location of residing objects gets reported moving, as soon as the measures taken are biased by secondary path reflections with increasing weight over time. Such effect is caused by simple averaging, and the effect indicates insufficient discrimination of first echoes. Standards ISO/IEC The basic issues of Rtls are standardized by the International Organization for Standardization and the International Electrotechnical Commission, under the ISO/IEC 24730 series. In the series of standards, the basic standard ISO/IEC 24730-1 identifies the terms describing a form of Rtls used by a set of vendors, but does not encompass the full scope of Rtls technology. Currently several standards are published: ISO/IEC 19762-5 2008 Information Technology, Automatic Identification and Data Capture Techniques, Harmonized Vocabulary, Part 5, Locating Systems, ISO/IEC 24730-1 2014 Information Technology, Real-Time Locating Systems, Part 1, Application Programming Interface, ISO/IEC 24730-2 2012 Information Technology, Real-Time Locating Systems, Part 2, Direct Sequence Spread Spectrum 2, 4 GHz Air Interface Protocol, ISO/IEC 24730-5 2010 Information Technology, Real-Time Locating Systems, Part 5, Chirp Spread Spectrum 2, 4 GHz Air Interface, ISO/IEC 24730-21 2012 Information Technology, Real-Time Locating Systems, Part 21, Direct Sequence Spread Spectrum 2, 4 GHz Air Interface Protocol, transmitters operating with a single spread code and employing a DBPSK data encoding and BPSK spreading scheme, ISO/IEC 24730-22 2012 Information Technology A. Real-Time Locating Systems, Part 22, Direct Sequence Spread Spectrum 2, 4 GHz Air Interface Protocol, transmitters operating with multiple spread codes and employing a QPSK data encoding and Walsh offset QPSK spreading scheme, ISO IEC 24730-61 2013 Information Technology Euro Real-Time Locating Systems Euro Part 61, Low-Rate Pulse Repetition Frequency Ultra-Wideband Air Interface, ISO IEC 24730-62 2013 Information Technology Euro Real-Time Locating Systems Euro Part 62. High-rate pulse repetition frequency ultra-wideband air interface. These standards do not stipulate any special method of computing locations, nor the method of measuring locations. This may be defined in specifications for trilateration, triangulation or any hybrid approaches to trigonometric computing for planar or spherical models of a terrestrial area. In SITS 371.1 2003, Information Technology, Real-Time Locating Systems, Part 1, 2.4 GHz Air Interface Protocol, in SITS 371.2 2003, Information Technology, Real-Time Locating Systems, Part 2, 433 MHz Air Interface Protocol, in SITS 371.3 2003, Information Technology, Real-Time Locating Systems, Part 3, Application Programming Interface. Limitations and further discussion. In RTLS application in the healthcare industry, various studies were issued discussing the limitations of the currently adopted RTLS. Currently used technologies RFID, Wi-Fi, UWB, all RFID-based are hazardous in the sense of interference with sensitive equipment. A study carried out by Dr. Erik Jan van Leeusch out of the Academic Medical Center of the University of Amsterdam published in a Euro unregistered trademark claimed RFID and UWB could shut down equipment patients rely on as RFID caused interference in 34 of the 123 tests they performed. The first Bluetooth RTLS provider in the medical industry is supporting this in their article. The fact that RFID cannot be used near sensitive equipment should in itself be a red flag to the medical industry. The RFID Journal responded to this study not negating it, rather explaining real case solution. The Purdue study showed no effect when ultra-high frequency systems were kept at a reasonable distance from medical equipment. So placing readers in utility rooms, near elevators and above doors between hospital wings or departments to track assets is not a problem. However, the case of keeping at a reasonable distance might be still an open question for the RTLS technology adopters and providers in medical facilities. In many applications it is very difficult and at the same time important to make a proper choice among various communication technologies which RTLS may include. Wrong design decision made at early stages can lead to catastrophic results for the system and a significant loss of money for fixing and redesign. To solve this problem, a special methodology for RTLS design space exploration was developed. It consists of such steps as modeling, requirement specification and verification into a single efficient process. See also, Indoor Positioning System, RFID, Track and Trace, Positioning Technologies, Context Awareness, Location Awareness, Multilateration, Real-Time Locating Standards, other related international standards, IEEE 802.15.4. References. External links, International Standardization in Engineering, International Standardization in Industry and Science, search page for ISO standards concerning RTLS, a real-time location search primer, International Standardization in Electrical Engineering, International Standardization in Communications, International Lobbying in Automatic Identification, U.S.-American Lobbying in Automatic Identification, Statement of International Lobbying on Real-Time Locating, ISO JTC1 SC31WG5 homepage on RTLS, ISO JTC1 SC31WG5 homepage on MIM, Company Driving International Standardization on, for example, RFID and RTLS in U.S., Schedule and actual scope of RTLS standardization in ISO JTC1, TC122 and SC31, Car-to-Car Communications Program funding of the European Union, RT Non-Line of Sight Localization System by CMR at UNSW, improve emergency or operating room efficiencies with RTLS, Medical Asset Tracking and Management using Rtls, Intro to Rtls Technologies, Gen 2 IR Technology in Rtls. Literature Malik, Ajay. Rtls for Dummies. Wiley. Pages 384. ISBN 978-0-470-39868-5. Indoor Geolocation Using Wireless Local Area Networks, Michael Warbaum, Local Positioning Systems, LBS Applications and Services, Krzysztof Kolodziej and H.J.L.M. Joan, CRC Press Incorporated.